Good morning, everyone. This is James, the chair of today's talk. Today we are very happy to have Dr. Clarice Poon as our speaker for the seminar series. So she received her PhD from Cambridge in 2015 under the supervision of Anders Hansen. After this, she spent some time in France and also Cambridge as a postdoc. And about 2 years ago, so she took up a current position as a lecturer of applied mathematics at the University of Bath. So she's a well-known expert on complex sensing and has made many fundamental contributions. The keywords including sampling, total variation, regularization, and also stochastic exam. And today, so she will talk about her recent research on bilevel learning for sparsity regularization. I think the floor is yours.
Thanks very much for the introduction. Thanks everyone for coming, and do interrupt me if you have questions. So I'm going to be telling you about a very simple trick you can do to handle sparse optimization. And so this is joint work with Gabriel Perret from ENS Paris. Okay. So the kind of problems I'll be considering today are of this form. So you want to minimize some regularizer, a sparse regularizer, plus some loss function, Ly, acting on x beta. So x here is a matrix, m by n, and y would be your data in Rm. So for example, you can think of Ly as the quadratic loss. And R here is typically a non-smooth function, which will promote some kind of structure. So for example, R could be the L1 norm to promote sparsity, or the nuclear norm to promote low rankness. And so this problem has been studied a lot over the last 20 years. And typically the way we deal with this is by somehow smoothing this problem in a clever way. So one particular class problems would be first order methods. And the way you deal with non-smooth optimization is to make use of Moreau-Yossi regularization. So instead of directly considering your non-smooth function R, you would consider its infemal convolution with this quadratic term. And what this in fact does is it turns this into a smooth guy. So for example, the L1 norm would be turned into this Huber function in red here. So probably the most well-studied class, most studied method here would be forward-backward splitting, where if your loss function is smooth, you simply do a gradient descent step on the smooth part, followed by a descent step on this smooth regularizer. And this method has been studied a lot, and there are many variants of it which have faster convergence. So for example, there's Pfister, or Pfister with restarts, or variable metric or quasi-Newton proximal methods, where instead of the identity here, you have some other metric here in this L2 term. And the reason why this is so popular is that it makes use of only first order gradient information, and so each iteration is relatively cheap. But first order methods are also relatively slow, so they only have sublinear convergence rate in general, and if you want, and under some strong convexity assumptions, you may be able to improve to linear rates. And forward-backward is only relevant when your loss function Ly is smooth, and when it is non-smooth, we would consider other types of proximal splitting methods, such as primal dual, Douglas-Thrashford, or ADMM. And so these two advantages and disadvantages also apply, but in addition, these other methods also have parameters that we have to tune, and this can be tricky in practice, and also acceleration of these other splitting methods, unlike forward-backward, is also in general non-trivial. So one of the motivations for our work here is that the use of quasi-Newton or Newton methods are very popular in smooth optimization because they have very fast convergence rates, so superlinear or quadratic. And what I will show you in this talk is how I can revisit iteratively weighted least squares and basically reformulate this to get a smooth bilevel problem. And the consequence of this is then I can make use of robust tools from smooth optimization like BFGS or conjugate gradient and obtain these nice convergence properties. And one difference is that instead of explicitly smoothing, I'm going to essentially reformulate this as a smooth problem, make use of smoothness that way. So let me first remind you what iterative reweighted least squares is by looking at this very simple lasso problem. Okay, so this is the lasso problem. So the loss function is simply the quadratic term here, and lambda is a positive number, regularization parameter. So IRLS is based on the idea of a quadratic variational formulation. So the L1 norm, you can essentially think of this as fitting a load of quadratics on top of this graph. So simply by Holder's inequality, you can see that the L1 norm is equivalent, can be written equivalently in this way. So it's infimum over all positive vectors eta of sum over beta I squared divided by eta I plus sum over eta i's. And if I took this formulation, right, and fit it and plug this back into here, then minimizing beta over this is the same as minimizing beta and eta, positive etas of this function here. And the thing you notice here is that I've got a 1 divided by eta I here, so this is going to blow up as eta I go to 0. And to deal with this, what people would do is they would regularize. So they add this red term here. It essentially adds as a kind of barrier to stop you going to 0. And if you look at this problem here, then it's very natural to think of alternating minimization. Right, so if you minimize over beta, this is simply a quadratic problem. So you minimize this guy here. So it has a closed form solution. And if you minimize over eta, then it turns out that eta also has a closed form expression. So this is iterative reweighted least squares. You simply do alternating minimization of these two and apply these two steps iteratively. Okay, and notice also that if you add epsilon here, then this regularization term, then you're no longer minimizing this guy here, but actually a smooth version of the L1 problem. And so what people do in practice, that epsilon goes to 0 gradually while you iterate between these two steps. So instead of adding this extra regularization term, I can handle this non-smoothness, the singularity, by essentially simply a very easy change of variable. So the idea is that I let v be square root of eta and u be beta divided by square root of eta, then if I look at this term here, that will be v squared, right? So I get my norm v squared here. And if I look at this term with this guy, then I get u squared. So the L1 norm is simply half norm u squared plus half norm v squared, where you had the map product with v is equal to beta. So that's the first easy thing I do. So if I plug this into here, then I can see that minimizing this lasso problem is the same as solving this problem here, right? This is my L1 term, and then I know that beta is equal to u had the map product with v. So the second thing I do after this reparameterization is this is now minimizing over u and v, and I'm going to put this into a bilevel form. Right, so I will say that minimizing this problem is the same as minimizing a function f, where this function f here is defined at the point v is defined to be the minimum of u of this guy here. And the thing to notice about this function f here, the two key properties, is that first, it is a smooth function, and second, it's now non-convex because of this term here. But it's actually non-convex in only a very mild way. Okay, and I'll say a bit more clearly about what I mean by this in the next slide. But the point here is that now I've got a smooth function, and I have at my disposal tools from smooth optimization, and I don't really have to worry too much about this non-convexity. So you can use, say, BFGS to minimize this function f here. Okay, so in terms of smoothness, so using very standard results from optimization, you can see that f is smooth and its gradient has a very nice formula. So in particular, its gradient is simply the gradient of this inner function here over v, evaluated at u, which minimizes this for a particular v. Right, so if I take the gradient of this guy here, then it's simply this guy here, and the u that you should evaluate it at is the u which minimizes this, which is simply the solution to a least squares problem. So you've got quadratic and quadratic here. Right, so it's easy to evaluate the gradient of f. And this idea, it actually is very, very well known in the literature. And so in particular, it links back exactly to the Varpro idea of Golub and Pereira from, I think even in the 70s they did this. And they would typically do this, put things into bilevel form, essentially project out some of the variables to handle nonlinear least squares problems. Okay, so it's smooth and we can compute this gradient easily by simply solving least squares problem. And second property is that it's non-convex, but only in a very mild way. So I'll just remind you of this very simple result that I'm sure you've seen already. But we say that v is a stationary point if its gradient of a function is 0. And it's called a strict saddle point if it's a stationary point, but its Hessian is not positive semi-definite. Okay, so essentially what it means is that if you're a strict saddle point, then you can always find a direction of descent. So you can always have an eigenvalue which is negative and find somewhere to go down. And there has been many works in recent years which show that strict saddle points are essentially harmless. So, so there are these previous papers which show how gradient descent essentially can escape these saddle points by injecting perturbations. Yeah. And for our particular function, if you simply evaluate the Hessian of it, which again is actually very easy to compute, is simply the Hessian of the full, you can is the short complement of the Hessian of your full function over u and v. So you simply do this computation, then you will see that actually all stationary points are either global minimums or strict saddle points. Okay, so yeah, so now we've got a function which is smooth and we can simply throw BFGS at it. And so let me give you some kind of intuition about what's happening if you minimize this smooth bilevel function f here. So here is just an illustration with lasso where I'm showing you the evolution of 10 coefficients. So n here, the size of my problem is 10. And yes, and this is and the x is simply talking to be a random Gaussian matrix. So on the left here, I'm showing what happens when you do forward backward. So in the case of lasso is simply iterative soft thresholding algorithm. So it's gradient descent in the smooth part followed by a soft thresholding term. And one property of doing this is actually the paths will be non-smooth in general. And on the right here, I'm showing you the evolution of the coefficients of your function f here. If you minimize this function f here. So if you do this using gradient descent. So there are two interesting things here. The first is that if you look at the paths of ISTA, then you have basically these kind of very linear paths and these non-smoothness here, these kinks here. And whereas if you minimize this function f here, is smooth, and then the coefficients basically go smoothly, well, they converge geometrically to 0. And the other interesting thing is that because of the soft thresholding operator, actually when your coefficients have to flip signs, then you will actually spend some time like stuck at 0 before you go away, whereas with this function f here, you basically jump over 0 in this very smooth way. And this second thing that I'm showing you here is if you look at lasso for deconvolution. So I've got Gaussian deconvolution matrix here, and I am basically taking finite and finite discretization. So n would be how fine I take discretization of my convolution. And here I'm showing you the objective area if I do gradient descent on this function f here versus ISTA. And on the x-axis would be iteration. So again, you see that if I let n go to, as I increase n, then actually the progress of ISTA in general will be much slower and slower, because what happens with ISTA, this has been studied in previous works, is that you have sublinear convergence rate, and at some point you have linear convergence, but then when n is very fine, actually you will be stuck at this sublinear convergence rate for a very long time, which is why you see this very slow behavior. And we have something quite interesting, I think, about handling this function f here, is that actually the progress of it is very fast. So even here is 150 iterations. This is 200 iterations, and this is 200 iterations as I go from n equals 50 to 2000. So essentially, this is basically the gist of my talk, illustrated on a very simple problem of lasso. So if you simply reparameterize, you end up with a non-convex problem, and then you put in the bilevel form, then you can simply apply BFGS, and in practice, this gives you a lot of computational gain. It can be very fast in general. So what I'm going to do now for the rest of the talk is essentially look a bit closely at these two ideas, and then show you that actually this is something very general and not just applicable to the lasso setting. So a few comments about quadratic variational forms. So actually quadratic variational forms, they are very well known in the literature. And I just like to mention, I think, 4 really landmark results here. So some of the earliest references I can find on this is in the computer vision community, and there's and the earliest theoretical result I found was by Gieman and Reynolds in 1992. So this paper here, and there they already describe a procedure to obtain a quadratic variational form given a regularizer. And their work is elaborated in this paper by Black and regularisation. And there they really gave many examples of regularizers where you can write things into a quadratic variational form, so both convex and non-convex functions. And these quadratic variational forms, they're really the basis of IRLS algorithms, and these algorithms were really widely studied in the around 2010s, partly because of the Boolean compressed sensing. And in the machine learning community, this is also known by subquadratic norms, or the eta trick. And what I'd like to show you in this next slide is essentially a result which encompasses all these works here, basically summarize when you can write a regularizer into a quadratic variational form. So if I have a regularizer, a function R here, then the following are equivalent. If R is of the form a concave function applied to beta squared, then it means that there exists a convex function psi such that I can have this quadratic variational form. Right, you minimize over beta I squared zi plus this convex function on z. And this convex function is simply the convex conjugate of minus phi, my concave function here. And when R is a norm, then actually the psi here can be written in terms of its dual norm. So, and note that actually here psi is convex, but R here doesn't need to be convex in general. So one example. So to show you an example, you can consider the Q norms, LQ norms with Q between 0 and 2. So you clearly see that if Q is between 0 and 2, then I can always fit quadratics above it, above this graph. So here, phi would be a function which looks like this, u to the power of Q divided by 2. And psi here is convex conjugate would look something like this. Right, so you can handle LQ minimization for Q between 0 and 2 using this way. And for the Euclidean norm, if you do the computation, then psi of z, you can see that it's 1 divided by 4 times the minimum over zi's. And using this, you can also look at group L1 norms. So if I have a partition of my indices 1 to n, and then this simply taking the L2 norm of each group, then R of beta, using this guy here, can be written in this way. So actually you see here, something you notice if you look at this a little bit is that once you take the minimum over z, then this actually forces all the zi's in each group to be constant. So in fact, this infimum over z is not really over Rn, but over Rk, where k is the number of groups here. So I can rewrite this guy here as the infimum over positive eta in Rk, where k is the number of groups, which can be much smaller than n in practice, of this guy here. So in the previous examples I showed you, essentially, I can always write, you can write, so the L1, LQ, or group norm, you can write a regularizer in this way. And what you notice is that you have this blow up at 0 as e to g goes to 0. And this is actually always inevitable. You will always have this if R is a coercive function, if it goes to infinity at infinity. So if R is a norm, then you will always have this blow up here. And you can get rid of this by doing a change of variable. So using this, you can simply rewrite R of beta as infimum over V Hadamard product with U equals beta of this guy here. So V is a vector over a number of groups in Rk, where k is the number of groups, and U is in Rn. And this is the group Hadamard product. And you can also have similar results in the matrix setting. So in particular, you can always have a quadratic variation of form if R of B is equals to a concave function applied to B transpose. So, and you end up with a quadratic variation of form looking like this, where you minimize over positive semi-definite matrices instead of positive vectors. So for example, in the case of the nuclear norm or trace norm, H here is simply the trace of Z. So again, you can have a desingularizing change of variable. So you can make a simple change of variable to say that RB is equal to minimum over matrices V times U equals B of Frobenius norm of U squared plus H of V transpose. Okay, so now that we have this quadratic variation of form, I'd like to say a few words about putting this into your bilevel formulation. So if we assume that L is a convex proper low semi-continuous function, a loss function, and our regularizer has a quadratic variation of form, and the H that we had in the quadratic variation of form is differentiable, then our sparse optimization problem is simply the minimum over V in Rk of f of V, where f here is defined to be the minimum over U of this guy here. Okay, and so, sorry, one comment I didn't make before is that when you did your change of variable, actually now you don't have any constraints when you minimize over V here, whereas before you did the change of variable, you had to constrain it to be, say, positive or positive semi-definite matrices. Okay, and notice that this guy here is actually a convex optimization problem. And if you write down as dual, then it is the maximum of alpha in Rm. So remember, our matrix X here is of size m by n of this guy here, where Ly is a convex conjugate of Ly. Ly star is a convex conjugate of Ly. And the optimal beta, V, and alpha can be easily computed from each other. So you have two ways of writing this f, and I guess which one you would prefer would be dependent on whether m or n is larger. Okay, so this function f is always differentiable, and its gradient is simply the gradient of this guy here with respect to v. Okay, and alpha here is a solution of the inner problem for a fixed v. So one comment here is that the gradient of f, it is always uniquely defined, even if alpha here is not unique. So if you look at this argmax problem, then actually it doesn't necessarily have a unique solution, especially if Ly star is not strictly convex. But because the gradient is only defined in terms of this guy here, where alpha appears, and I've got this quadratic term here, which is strongly convex, then it means that this guy here, it is always unique, whichever value of alpha I plug into here. And the second comment is that if Ly is differentiable, then I can also write this gradient, not just in terms of gradient of this with respect to v, but I can also differentiate this with respect to v. So you can have a different way of writing the gradient of f in terms of the first problem I showed. So u here is a solution to this minimization problem. So you see that actually u here is unique. So there are two cases which I especially looked at, and they are lasso and basis pursuit. So lasso is this problem we just saw, and then you let lambda go to 0, then we have this basis pursuit problem. And in terms of gradient of my bilevel function f here, it is this guy here, and the inner problem alpha is simply the solution now to a least squares problem. And something which I think is quite interesting here is that this gradient computation is relevant for both of these problems. Right, if lambda equals 0, I simply set lambda equals 0 here. And I think this is something which is a bit different from existing methods, because in existing methods, you have to deal with these two problems using different methods in different ways, right? You have to set up your optimization problem differently to solve this. And whereas here you can handle lambda equals 0 in a very seamless way. Okay, so as few remarks, you can let lambda go to 0 seamlessly. And the second remark is that to solve the inner problem, you simply have to invert a linear system which is symmetric and positive semi-definite. Okay, so you can either directly invert it, so it's minimum of mn cubed computation, or you can apply conjugate gradient. And the outer problem is a smooth unconstrained problem, so you can apply BFGS to it. And this in particular will give you local superlinear convergence. So there are basically 4 key ingredients to this done. So the first is that we make use of the quadratic variational form. And the second is that you reparameterize this to get rid of the singularity that you get from doing this. And then you put in the bilevel form. And finally, it means that you can do higher order methods on it, so BFGS. And just a couple of remarks about what happens if I get rid of some of these ingredients. So for example, if I don't reparameterize, but simply put my user quadratic variational form and put into bilevel form, then apply BFGS, this is possible. So if I simply make use of the quadratic variational form, then actually this now is a convex problem, and you can rewrite this inner problem over beta here, rewrite in as dual, and then you can see that is the same as minimum over eta and maximum over alpha of this guy here. So in fact, this function f here, it is also a smooth function, and you now can apply BFGS on the positivity constraints. So one difference with what we've done is that if you plug in reparameterization, is that we have a non-convex formulation, but it's got no constraints, and you can simply apply standard BFGS, which is simpler. And the second comment is that here you can do BFGS because the constraint is easy, but then if you have a function over matrices, then this constraint is more complicated, say as the minimum over eta being a positive semi-definite matrix. Okay, so then you will be restricted to first order methods. And so this particular form has been done in the case of a trace norm in this previous paper. And in general, actually, I observed that doing this can lead to much slower convergence in practice. So if you come back to my experiment with the Gaussian deconvolution example, as I let discretization increase, then when discretization is relatively small, so n equals 100, there is not much difference between our non-convex formulation, non-convex pro, and quadratic variational form. But as you increase this discretization, then actually you will see that the performance of this quadratic variational form will deteriorate with n. Okay, and the second comment, what happens if I get rid of this bilevel form? Okay, so if I simply reparameterize on the quadratic variational form, you can consider the minimum over u and v simultaneously and apply BFGS to this, or you can apply alternating minimization. So the comment here is that in general, this is worse than putting things into a bilevel form, because actually the computation effort between the two is, if you consider alternating minimization, is the same. But the Hessian of the projective function f here will be the short complement of the Hessian of this function here. And we know that a short complement will always have a better condition number than its full matrix. So in this sense, it is nicer to handle f than g over u and v simultaneously. Okay, so let me show you some benchmark illustrations. So the set of illustrations I want to show you will be for lasso. And I will show you comparisons against 10 different methods for dealing with lasso. So the first three, they are essentially forward backward type methods. So we consider proximal quasi-Newton methods, where you put a variable metric into the quadratic term when you compute your prox. Pfister with the BB step and restarts, and the spectral projective gradient. And 4 and 5, they CGS and Seller, they are essentially methods which handle prune your support in a clever way. So CGS is an active set method by Goldstein. And Seller is a coordinate descent method with support pruning. And we'll also compare against an interior point method. Is from the group of Stephen Boyd. And the last four are essentially other ways in which you can imagine doing BFGS. So you can do directly quadratic variational. So this is simply doing LBFGS with positivity constraints without non-convex reparameterization. So it's option 1 that I mentioned previously. Alternating minimization on my fully non-convex formulation. So this is the way I have G over U and V, and I simply minimize U followed by minimize V. So this corresponds to solving linear systems over U, then over V, and so on. And yeah. And we can apply LBFGS on my non-convex formulation directly over U and V, as I just mentioned. And finally, this is specific to lasso only. You can consider applying BFGS with positivity constraints to this guy here, which is probably the way people will have most naturally thought of applying BFGS to lasso, right? So you can rewrite lasso in this way. So beta is equals U minus V, where U and V are positive. And the L1 norm is simply the sum of these guys here. Okay, and in terms of benchmarks, I'll show you just 4 examples here, and they are data sets taken from the libsvm website, but there are more in the paper if you want to look. And so some observations that you will see in the slides coming up is that you see the outperformance. I'll show you comparisons for different values of regularization parameter lambda. And you see that the performance will be relatively robust to your choice of regularization parameter. And in general, Pfister and coordinate descent pruning typically perform very well with large lambda, but you see that in some cases they break down a bit as lambda goes to 0. And in most of the following numerics, you will see that this combination of this non-convex reparameterization plus bilevel reformulation is really the key to fast performance, and this will in general be faster than the other ways of applying BFGS. Okay, so this is the first data set that I looked at. So number of samples is about 22,000 and 122 is the problem size. So our method, non-convex pro, is this dotted blue line here. Right, so lambda star is the optimal regularization parameter found by cross-validation. So it's the smallest mean squared error. And I'm showing you different lambda as different factors of lambda max. So lambda max is the largest regularization parameter take before your solution becomes trivial. Right, so this is going from large regularization parameter to small regularization, so half, 1/10, and 1/50. And this is the optimal one. So dark blue as our method. Here you can look at, say, Cellar, which is the coordinate descent with pruning. So it's very fast. It's this guy here. For large regularization parameter, but you see that it deteriorates right here. And here, as I let lambda become smaller. In this case, the forward-backward type algorithms, so these first 3 here, they all perform relatively well. So there will be the black line with circles, this blue line with crosses, and this blue line with stars. So you see that in all the graphs, they are relatively fast. Quadratic variational, where we don't do the reparameterization but apply BFGS with positively constrained. You see as this yellow lime kind of line here. Alternating minimization is this orange line here. So you see that's always slower. And this here. Yes, and here actually doing LBFGS on the positive problem is actually quite fast here. It's quite comparable to our method. Okay, so for the next set, here the number of samples is much smaller than the problem size. Our method is again in dark blue. And here actually Celler, the coordinate descent with pruning, it is very fast throughout. It's actually the fastest method throughout. You notice here that actually the forward-backward algorithms don't perform as well. They perform very well when the regularization parameter is large, and you see that they deteriorate. So this is with the variable metric, the quasi-Newton proximal method. And Vista with restarts is here, whereas it's quite fast when regularization parameter is large. Okay, alternating minimization is very slow here. And here actually you see that doing LBFGS in the most natural way, just with positive constraints, performs less well than the last one. And the next two are similar. But something you can notice here is that our method, even though it isn't always the fastest, it is very consistent throughout, whereas the other ones, it seems that they are they're much more fragile to the problem and the regularization parameter. Okay, so the next set of examples I want to show you are group lasso. So this is for MEG and EEG brain data. So here what you want to do is you want to locate source locations in the brain. And next here's a forward operator where the number of columns is about 22,000 and they correspond to source locations. And there are 360 rows in this matrix corresponding to MEG and EEG sensors. And actually each sensor to locate your source location, you have time series data. So there are 181 time points. So Y here is your observation. And so this is an experiment setup taken from this paper by Nidayi. And what you want to recover is this matrix W here. And here you're assuming that the source don't move around, so they're stationary. And so what you expect is that your matrix W here has very few rows activated, which is why you would apply a group, a one norm with L2 under each row. So here I'll just show you the comparisons against the forward-backward type methods and Celler coordinate descent, since they were the fastest type of methods that we saw earlier. So, and this is for different lambdas as well. So large lambda going to smaller lambda here. So our method is again this dark blue dotted line, this blue dotted line. And again, you see that the performance is quite robust to the choice of regularization parameter. Even when regularization parameter is very small, it's less than 10 seconds to get to convergence. Zero mem SR1 is the quasi-Newton proximal method. So it's this black line with circles. Celler is again coordinate descent with pruning. And Vista is this light blue line with crosses. Okay, so you see that when lambda is large, all methods perform relatively well, but these other methods, they deteriorate when lambda gets smaller. Okay, so the next set is nuclear norm. So here we'll consider multitask feature learning as proposed in this previous work. And here what you want to do is you have a load of tasks, capital T tasks, and for each task you want to fit training data to some observations, some labels. And the learned functions are simply linear functions. So this, as explained in this paper, it can be dealt with by nuclear norm minimization. So the nuclear norm minimization over W, which corresponds to the where each column corresponds to each task, is essentially encouraging your task to share a small number of features. So for example, you could be trying to predict the performance of students at different schools. So each T will correspond to a school. Okay, and in our setting, our non-convex reformulation would be minimizing of a bilevel function of this form here. Okay, so to handle this in a problem is simply having to solve a linear system. And what we'll compare against is iterative reweighted least squares, which is the method which is often used for dealing with this problem. So with iterative reweighted least squares, you would put in your quadratic variational form, but you would put in this regularizer, which acts as a barrier to keep D being invertible. So a comment is that the per iteration complexity is the same for both methods. So with iterative reweighted least squares, to solve for W, you also have to solve a linear system of the same size as our guy. But one advantage of our scheme is that we don't plug in extra regularization, so there's no need to tune your epsilon. Okay, so this is showing you convergence plots for 3 popular data sets used in multitask learning of different sizes. So here I'm also showing comparisons against Vista with restarts, which is this black line here with circles. Our method is this blue line, blue dashed line. And all these other lines, they are iterative reweighted least squares with different regularization parameters. Okay, and again, you see that we have very fast convergence in at least these two. This one is less good, but then all methods are performing relatively well, and it's essentially a much smaller problem, and everything's converging in about 0.2 seconds. Okay, so the next example is related to basis pursuit, so is computing an optimal transport distance. So the Earth mover distance, and is also called the Wettstein-1 distance, is a distance between probability densities, and it can defined in this way. So you minimize over a flux vector M here, and this is divergence, and alpha and beta are your probability densities. And essentially, this problem, after discretization, you can simply see it as a basis pursuit problem. So you minimize an L1 type regularizer subject to linear constraints. So here's linear constraints, and if the dimension of your problem is 1 or your graph, then it is simply L1 regularization here, or group regularization if D is greater than 2, greater than or equal to 2. Okay, so I'll show you some examples on the graph. So it simply corresponds to lasso. So on the graph, A and B would be probability vectors, taking values on nodes, and M, your flux vector now takes values on the edges, and D is your gradient operator. So this here can be rewritten as this smooth bilevel problem. And notice that you were actually turning this constrained optimization problem into simply a descent problem. So the gradient of F is easy to compute. And actually here, the linear system that you have to solve is a weighted Laplace problem. Okay, and for this, actually, there's a lot of efficient solvers. And essentially, to invert this is no longer n cubed, but actually linear with n up to log factors. Okay, so this is showing you some examples on computing this distance on graphs, and we'll compare against primordial and Douglas-Rashford, which are popular proximal splitting methods for dealing with this kind of non-smooth problem. So in the brackets here under each graph, the first number is the number of nodes, and the second number is the number of edges. Our method is again this dark blue, this blue line with dot, this dashed blue line. And all these other ones, they are primordial or Douglas-Rashford at different parameter choices. So you see that actually with these other methods, the performance can be very good in practice, but then it's very sensitive to your choice of parameters. And it's not always easy to tune this. Whereas what we're proposing is a much simpler way of dealing with this kind of optimization problem, because there's basically nothing to tune here. Okay, so this is the last example I want to show, and is for non-convex LQ minimization. So we can consider this non-convex problem, and writing in the bilevel form is equivalent to minimizing a function f defined in this way. Okay, so for this to be differentiable, I want this guy here to be greater than 1. And this is the case when q is at least 2/3. So the bilevel function is smooth when q is not too small. And essentially, this is a very simple descent problem here, and standard results in literature will tell you that any descent method with line search will guarantee convergence to a stationary point. And as far as I know, the main way to deal with this kind of problem here, where you have this linear constraint, would be with iterative reweighted least squares. But here you can have a different way to handle this non-convex guy by doing smooth optimization. Okay, here it's just a result of minimizing this function, and it's showing you the phase transition for random Gaussian matrices. Okay, so this is over, I think, 100 instances of random Gaussian matrices, and showing you what happens when you increase the number of samples against successful recovery. And as you expect, the smaller q is, the better recovery you have, the higher the chance of recovery. Okay, so that's it. So this talk is actually very, very simple. I told you, if you can simply reparameterize in a very straightforward way, stick into bilevel form and put BFGS on top. And then in practice, this can give you a very good performance. So typically for compressed sensing problems, where you have, say, the RIP, restricted isometric property, or Nonsmooth property, then as you saw in a lot of my numerics, Pfister type methods or coordinate descent, they perform very well. So when things are nicely conditioned. But one nice thing about what we're proposing here is that it's very simple. There's no real parameters to tune, and it's also seemingly very robust to different problems and different regularization parameters. So this talk is based on this preprint, which is on arXiv, and we also have code for you to test out. So thanks for listening.
Okay, thank you very much for a very nice talk. So I think we have plenty of time for questions. Any questions from the audience?
I think
Okay,
Sylvia.
Yes.
Yeah, I have one question.
Yes.
Yeah. Thanks all for the very nice talk. I was wondering, these examples that you show, is there any you use the conjugate gradient for the GAN computation?
In the examples I show, no. So everything we just use backslash in MATLAB.
Yeah, I was wondering if there is room to check, I don't know, how the conjugate gradient, for instance, behaves when you advance with the iterations for your upper level function, right? If but yeah, is it something you have been looking at?
Can you say your question again?
Like when you have to solve this sequence of normal equations, essentially, if you use a conjugate gradient, I was wondering, you may have a different performance of conjugate gradient as the system of normal equations varies as you go ahead with your solver iteration, essentially. And that was
because you're not solving exactly, so you have this.
Exactly, but also the metrics involved in the normal equations will be different, right? As the iterations.
Yeah, so I don't show any numerics here or put them in the paper, but I have tested with conjugate gradient or other ways of dealing with the inner system one is when you can't directly invert it. And in practice, what I would do is I would fix it for a relatively low number of iterations. And as we progress, for a lot of the problems where this does perform well, actually you will have convergence of conjugate gradient in 10 iterations.
Oh, that's
so
impressive.
But for the some problems that I tested, so of course this is problem dependent. But yes, I would say that this method it may not perform well if your inner problem is difficult to solve or if you have to apply many iterations of conjugate gradient. But in a lot of the test problems I've tried, actually what I just do, there's no real kind of theory or anything smart to say about this, is I set it to be a very low number of iterations, and essentially it kind of fixes itself as it goes along, but I don't have anything smart to say about this. So yeah.
Thank you very much. Yeah.
Thank you. Matthias.
Yes, it was like a very nice talk, Clarice. Really enjoyed it. I've got a questions regarding sort of like when you can apply this method to a problem. So I think there were, two cases which were not clear to me whether they are covered or not covered. So one of them is if you have something like a total variation type problem or total generalized variation. So what about that?
So for total variation, if you were to write it down, then actually the inner problem to solve is a kind of complicated linear system.
Okay.
So I haven't tested it numerically. I think you can do it, but then the linear system you have to deal with is not as nice.
Okay, and so like, can you like roughly say like what is the linear system that you have to solve? It's probably then related to like the gradient and the divergence operator, I suppose.
Yeah, so it's the linear system involving both X transpose inverse and your divergence. Yeah, so I haven't actually looked into this in great detail. And
so then I guess like likewise, if you were, for instance, to apply this approach to the data fit, let's say like you have like a linear image problem, and instead of having a quadratic loss, you want to have, I don't know, like the L1 loss, I guess, and so like the same would apply, that you then always have to have a linear system that involves a for operator. Okay, so then maybe like, yeah.
So yeah, L doesn't have to be the quadratic loss, and you can always write this in terms of the conjugate gradient. Mm-hmm. It's just that this inner system, it's not a linear system. It doesn't have explicit form anymore.
Okay.
So these two are specific cases where your inner problem is very easy to handle. But of course, you can have different constraints. So even if you put, say, positivity constraint on this, on your beta, then your inner problem is no longer straightforward to handle. And you would have to do other things to handle the inner problem. So whether this works well or not depends on whether you can, whether the inner problem can be handled well.
Okay.
So, but you still have a smooth optimum. You can still put in a smooth bilevel form. It's just that whether it's easy to compute your gradient or not.
I've got a question sort of like related to your comment, and that also like might be a bit related to Sylvia's question. Not sure about that. So because like in the end of the day, you have this like this bilevel structure, and then like in some sense, kind of like the algorithm you're using is kind of alternating in a way, right? computing the gradient needs to solve a system of linear equations, right? And then you do a gradient-based update, for instance, in BFGS. And so what if, because I think like sort of the potential methods you could apply, I think, so you said like you could like do alternating minimization, really solving for, I don't know, I think you call this U and V, alternatingly, and then like there were a few options. There's one option that I would consider quite natural, I think that you didn't mention, which is to just like do some sort of like descent update in each of the variables rather than really solving for each of them alternatingly. So like, let's say like alternating gradient descent or something. Or was it covered in one of the options?
All right, so instead of, so here, if you look at this problem, if you minimize U over U as a quadratic problem, and similarly with V as quadratic problem, and you would instead do a descent step in U followed by a descent step in V.
I mean, as an option, yes, exactly. Like without solving any system of linear equations, exactly.
And what would be the advantage?
Well, that you don't have to solve systems of linear equations. That you sort of like have like cheap updates in both U and V. And like you have cheap updates, I guess, like no matter what your linear system involved is. I mean, whether these are the like good updates, I guess like that's yeah, will need to be tested, but at least like there are like cheap updates.
I would say the disadvantage of dealing with this full problem in general, and there's one reason why people project onto a smaller set of variables, is conditioning, is problem conditioning. And I think the issue that you're seeing here, or this comparison against alternating minimization versus our descent method, is not really to deal with the difficulty of inverting matrix, because it's not too bad here in these examples.
Okay.
So the issue you're seeing here is much more to do with conditioning.
Okay. Thank you.
Okay, are there any other questions from the audience? So from the room, I think there's one, so please maybe you can go to the microphone and
Sure, I'm not sure how it works here, but can you hear me, Clarice?
Yeah.
Oh, it does it automatically. Wow. Fancy technology here. Thank you very much for the very nice talk. Definitely agree with what everyone else has said. I was also interested in the conjugate gradient question, but one question about the theory part: when you rephrase the problem as a non-convex problem, is there any risk that you can introduce, or is there some hypothetical risk? I guess in your numerical results, it didn't seem to occur at all, that you introduce some sort of artificial stationary points that are not in your original problem, or is there, can you, with some theory, basically argue that those cases cannot occur? Maybe you have said something about this, and maybe I missed this, but just
for group lasso.
I mean, or for any of. Sorry. Yeah.
Well, for any of the, I've never observed you being stuck. But in terms of theory, you can, for group lasso, you can compute your Hessian, and you see that the only stationary points are either strict saddle points or global minimums. The only place where I do see issues with non-convexity is where the problem is non-convex to start with.
Sure.
So with LQ minimization, if you put it into a non-convex form, then actually if you like, as Q goes to the limit of 2/3, then actually it becomes more and more non-convex. And there you do see issues where you set up bad stationary points.
Okay, thank you.
So actually for this graph here, for Q being smaller, as I go to this limit, actually I generate 10. I solved, I generate 10, I solve it 10 times with random starting points and take the best one.
Okay. I see. Thank you.
are there any more questions from the audience? So if not, so okay, please go ahead.
There is one here.
Yeah. Can you hear me? Yeah.
Oh.
Yeah.
Oh, well. So for your method, do you need to choose the regularization parameter ahead of the iterations? you can change it.
You mean there is no regularization parameter?
Like the one on the minimization, like the one on the, yeah, when you formulate the optimization problem.
All right. Yes, I assume that this lambda here is given.
Yeah.
Is that what you're asking?
Yeah, yeah. I mean, if there's any way of updating that throughout the iterations, like could you change that throughout the problem, or you have to assume it's given?
I did not look into this because here I'm just considering a case where I'm solving the optimization problems of this form, and I wasn't really so much interested in those problems where you really look for smart ways of tuning your regularization parameters. Yeah.
Okay, thanks.
Any other question from the audience? So if not, I think I cannot see very clear. Martin, are you still asking questions? I see you raise your hands.
No, I was just scratching my head.
Okay. Okay. Otherwise, I think we will finish it. Let's thank the speaker again for the very nice talk. Okay, I think.